Hello, and welcome back to our continued conversation on polar coordinates and polar graphs. In the previous conversation, we got through discussing and introducing what I'm now going to call the circle family of polar curves. Remember that this entire chapter is on parametric equations, or rather parametric curves. And I just want to gently remind everyone that this conversation in polar curves is still the conversation on parametric curves. And the relationship can be spelled out in the following way. If we're given any sort of polar, I say polar equation here, but really this is just any sort of polar curve, for example, r as a function of theta. Since r here is a function of theta, we can take any kind of parametrization of a given curve, say x, y coordinates, if we use the the polar conversion that x is equal to r cosine and y is equal to r sine. Those are the identities that we had from trigonometry lifted from the first page of this handout. Then we can replace the r here with this associated function of theta that we're working with, the polar curve, and that immediately gives us a parametrization of our xy coordinate curve in terms now of only thetas. And therefore we have one unique parameter that can run around, and then that can spell out or draw whatever this curve looks like. So this notion of parametric or of polar curves really is a special case of a parametric curve. It just happens to be one which is modeling any sort of situation that has a lot of curvature to it. So with that said, we have already seen the circle family. And just as a gentle reminder of what we had discussed previously, if r is equal to a, what that means is that theta is allowed to be whatever it wants, and in particular, at all instances, remember this r stands for the radius, so what this means is that at all instances, the radius must be fixed at a. And at that case, what that means is that we're centered here at 0, we go out to a radius of a, and then theta is allowed to be anything it wants. And there you have it, we have a circle of radius a centered at 0. Or 0, 0, I should say. Now, I haven't said anything about where this parameter ranges, this theta that we're talking about here. Very frequently, it'll range between 0 and 2 pi. And what we might have seen in the previous conversation was that, indeed, if we shift from a circle centered at 0 to a circle tangent to the pole, then indeed we end up with a situation where the polar curve might get traced out not once, but maybe twice. Well, if we haven't seen that yet, we will in the next example. For now, I think what we did just discuss was the fact that 2a sine theta is exactly going to be a curve tangent to the pole, pointing upward, so therefore it looks like this. Specifically, again, of radius a, and therefore the diameter is 2a. So this 2a right here is representing the diameter. And the sine value is what tells you that you go up, much like the unit circle, whereas if it was a cosine, then indeed we go horizontally. So in this case, we start off positive horizontal, and then we move tangent to the pole, again of radius a. So these are called the circle family, obviously, because they generate circles. The way we would have drawn these before, in the previous pages, is by taking each of these equations and then converting them into their Cartesian form and then unpacking what that meant. In some sense, what that means is that we're shifting from the parameter being theta back into x's and y's. So in some sense, we lose sight of what theta is doing to draw these pictures. So probably what we need to do is we need to develop a more steadfast way to draw these pictures that relies more on what theta is doing and less on being able to convert it into Cartesian. Because what we saw earlier is that converting to Cartesian is not always the most straightforward task, especially when your polar curve is a little bit more complicated. So what we're going to do is we're going to zero in on these two examples. Maybe we'll look at this one. And we're going to redraw this, but we're going to do it more from this original formula here. We're not going to use any sort of x's and y's along the way. And what we'll see as we proceed is that this idea that I was floating, this idea of tracing once from 0 to 2 pi, tracing twice from 0 to 2 pi, this will start to make a little bit more sense. So let's take a look. Here what I'd like to do is I'd like to graph r equals 6 sine theta, but I'm going to do it without converting to x's and y's. Instead, what I'm going to do is I'm going to start by graphing what I'm going to call the Cartesian form, which feels a little confusing because I'm saying we're not going to x's and y's. But when I say Cartesian, what some people will replace that phrase with is what's called the quote-unquote flat curve. The idea here is that instead of wrapping everything together into a nice curvy polar graph, we instead look at what's happening before we wrap it all up. Meaning what we're going to do is we're going to graph this function just as if we were in a regular old trigonometry class. So over here on the left, we have two axes. The input variable, the independent one, is theta in this case. The output, the dependent variable, is r in this case. And if I were to just graph a 6 sine theta, we know that that's going to look like, well, it's one period of a sine graph, and its amplitude is 6. So it goes up to 6 and down to -6. Note that this goes all the way out to the theta here being 2 pi. We know that halfway through is pi. And we know that 3/4 of the way through is 3 pi over 2. And 1/4 of the way through is our pi halves. Those are each of our quadrants. And what I'm going to do is I'm going to very, very carefully figure out how this graph translates to a polar graph as theta moves from 0 to 2 pi, and we track what the radius r should or should not be doing. So let's take a look over here. So what we're going to do over here is I'm going to start with theta equals 0 is pointing in this direction, right? And remember, as theta sweeps across this x-axis, or I should say the horizontal axis, over in the polar world, the theta is starting to rotate in a counterclockwise capacity. Notice that we start this entire problem, let's see, theta is 0 here, so that's the coordinate r theta is equal to, it looks like 0, 0. So that means that when I'm pointing in the 0 direction, my radius is also 0, which means I'm starting down here. Interestingly, as I move from 0 to pi over 2, meaning specifically, as my theta ranges from 0 to pi over 2, as I make that sweep from right to left, my radius needs to go from 0 all the way up to, let's see, what is this point? This point is the r theta point given by 6 comma pi over 2. So what that means is that by the time my theta hits pi over 2, my radius has increased all the way to 6. So that means all the way up here at 6, my radius starts at 0, and as I make that sweep, it seems to increase until it hits 6. And so with this identification, I can look at this and say, okay, so this part of the curve right here is being identified with this quadrant of the sine curve over on the left. Now after that, as theta ranges from pi over 2 to pi, so we continue our sweep through the second quadrant, my radius drops from 6 all the way back down to 0. So that's going to be this point right here. This is going to be 0 comma pi. And that's going to correspond to, well, my radius needs, or my r, needs to go from 6 as I sweep through quadrant 2. It needs to go from 6 all the way back down to 0. So that's going to have this effect. And we have my pink point there at the origin as well. So what I see is that over here on the left, I have that second quadrant. Now, on the surface of it, it looks like we've drawn this curve right here. We know that it points up because it's a sine function, and so we're looking at this, we say, okay, this is 6a, So that means it has a diameter of 6. Okay, everything's looking great. But the thing to notice is that over here on the left, I've managed to go through the first quadrant, giving me the right side of this. I managed to go through the second quadrant, giving me the left side of the polar curve. But whenever we're looking at this, the basic assumption is that we're graphing this specifically on 0 to 2 pi. So I've already drawn one full circle, and yet I've only gone pi units. What about the whole second half of the sine function? Well, let's see what happens. So currently, at this moment, I finished graphing through quadrant 2, so I'm facing this way to the left, and I need to traverse quadrant 3. As I traverse quadrant 3, so I'm looking in this direction, the bottom left, as I do that, my radius seems to be going all the way from 0 down here it says -6. So this is the point r theta is equal to -6 3 pi over 2. So that means that by the time I hit 3 pi over 2, which is the end of quadrant 3, so now I'm facing down here, my radius needs to have gone from 0 to -6. The negative is important. Remember, the negative radii means that you walk backwards. So as I move through this third quadrant, my radius increases from 0 to 6 units backwards. What that means is that, in fact, my curve retraces the same line it just traced out here in the first quadrant. Meaning that, for example, this part of the curve, highlighted in red, is actually the same curve over there on the right. Similarly, what I have is that this part of the curve, the fourth quadrant, is actually the same as the second quadrant. So the notable thing about this particular curve is that, in fact, this right here is actually traced twice from 0 to 2 pi. And that was one of the more quirky things that I was starting to observe earlier, is that in this case, when I turn around and I go from the flat curve to the polar curve, I can see that this graph right here is traced twice from 0 to 2 pi. Similarly for this one on the right. Whereas this one on the left, you can verify for yourself via this entire method, this is only going to be traced out once. And this is going to be important for us once we start computing areas. So the circle family can be thought of in exactly this sort of identification with the so-called flat curve. But it turns out that really any polar curve can be drawn this way, and that you can leverage your knowledge of graphing and trigonometry to achieve graphing in polar. Let's do another example. So we just learned about the circle family. Let's move from the circle family to what we'll call the rose, sometimes called the petal family. You'll see why once we do an example. The notable difference here is that now I have, say, 3 cosine 2 theta, or here I have 3 sine 3 theta. So compared to these circles up here, the inside angle theta has now been amplified by a 2 and a 3. Now, if you remember this from your trigonometry, what that means is that our period is actually compressing. So that means, for example, in this function, we're going to get 2 cosines from 0 to 2 pi instead of our traditional 1. Let's take a look at that flat curve. So over here, we're going to have theta, we're going to have r. The 2, again, means that the period is equal to 2 pi over 2, which is equal to pi, which means we should get 2 cosines from 0 to 2 pi. And indeed, let's find out. So there's going to be, remember, cosine starts high, right? So we're going to end up with 1 cosine and 2 cosines. Now, what you might have noticed in the previous problem is that every time we had a bump of some sort, it built sort of like one of these circles. We're now going to start calling those petals. So what that means here is I have half a petal, a full petal, a full petal, a full petal, and half a petal. Now up here, we notice that the petal stopped and started at whatever these points were, the red and the pink one. The red and the pink one turned out to be those horizontal intercepts. So in this problem, it might be worth it to figure out what those horizontal intercepts are. The way you can solve for those, if you want to do a little bit of scratch work, is we need to solve for when r, the vertical quantity, is 0. But that means that's when the function 3 cosine 2 theta is equal to 0. This is, well, let's see, when does cosine vanish? That's going to be when its angle 2 theta is given by anything that points up or down. For example, pi over 2, 3 pi over 2, 5 pi over 2, and 7 pi over 2, for which when I divide by 2, I get pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4, all of which are from 0 to 2 pi. This conversation is something that I would typically spend longer on in a pre-calc class, but we have seen that before, so I'm streamlining that. So what that means is that if I come over here on the left, I have 4 such x-intercepts. Pi over 4, then we have 3 pi over 4, then we have 5 pi over 4, then we have 7 pi over 4. We know that the radius here is a 3, and it goes down to -3. So if I come over here and I draw out my polar curve, I start by saying that at an angle of 0, I have a radius of 3. So this starting point right here is actually going to be over here. That's going to be all the way out at 3. And I see that by the time I hit pi over 4, 45 degrees, my radius should shrink from 3 all the way down to 0. So as I sweep over here on the right, from 0, that's theta equals 0, to pi over 4, that's this angle right here, that's theta equal to pi over 4. As I sweep through that part of my polar region, my radius should go from 3 all the way down to 1. And there you have it, that's half a petal, half a petal. So I can come over here and make that identification. So I'm going to call that 1, call this 1. Then what we have is that between pi over 4 and 3 pi over 4, 3 pi over 4, of course, is halfway through quadrant 2. What I see here is that my radius needs to actually go down to -3, which, as we saw in the previous problem, means I need to walk backwards. So as I sweep now in this region right here, my radius is actually backwards, so I have to walk backwards. So actually there's this reflected copy of what we're considering. And if I sketch my graph through the backwards region, I see here I have another petal made up of 2 half petals. So for example, if I were to cut this in half, here's 2, here's 3. Over here on the right, I'm going to end up with a petal, say, here. And there you go, comprised now of 2 and 3. Then from 3 pi over 4 to pi over 4, I have another petal. If I go ahead and cut that in half, label that 4 and 5, you can even note that between 3 pi over 4 and 5 pi over 4 is pi itself. So that's going to produce this petal over here to the right. Or to the left, sorry. Coming from numbers 4 and 5. Again, my angle theta is moving counterclockwise. Here we have another negative petal, but by this juncture, I'm already moving through the bottom of the graph over here on the right. So that means as I walk backwards, that's actually going to graph in the top part of the graph, which is going to give me this petal. If I were to cut that in half and call that 6 and 7, we're working with 6 and 7. And now we see that from 7 pi over 4 to all the way out here to indeed 2 pi, that's going to be this final sweep right here on the right, all the way on the right of the polar graph. My radius is going to go from 0 back up to 3, and predictably, that's going to be the other half of my initial petal. If I call that 8, we have that. We've now finished the whole picture from 0 to 2 pi, and we see that we have built something that looks a little bit like sort of some petals on a flower, hence the rose/petal family. One thing to note while we did this was that, in fact, there was no tracing over itself. In this problem right here, indeed, here we've only drawn once, or it traced itself once from 0 to 2 pi. Which is a little different from, for example, these ones up here that were traced twice. So clearly there's something going on in the background. We'll make that more clear before long. And so this is the utility of graphing everything using this flat curve first, is that we can translate it to the polar curve really, really easily just by carefully mapping where the different quadrants go. Now, what's going to be of no great surprise is that notice that we have a 2 here. What we're going to make as an observation before long is that since there's a 2 here, we're going to note here that 2 is even, and that we see 4 petals. That's going to be something we're going to come back to, but that's an observation. 2 there is even, and we see 4 petals. That's twice as many. We see 4 petals. Now, what we're going to do is we're going to look at a sine function instead, and we're also going to look at a situation where instead of this number here, 2, being even, we're going to look at what happens when it's odd. So let's see what happens here. As we saw before, we're going to draw this picture. We see that our period now has been compressed even further by now a factor of 3. So that means from 0 to 2 pi, I'm actually going to get 3 sine values. So we're going to get 1 that goes up and down. Then we're going to go up and down. Then we're going to go up and down. And there's my 3 sine functions. We're going to go up to 3 and down to -3. So that's going to be the length of our petal, just like we saw before. It is going to be worth finding those x-intercepts. We can do the same thing as we did before, like what we had up here. If we went through that process, what we'll find is that, in fact, our horizontal intercepts are going to be at pi over 3, 2 pi over 3, 3 pi over 3, which is pi, 4 pi over 3, 5 pi over 3, and 6 pi over 3, which is, of course, 2 pi. This is our theta r axis, so let's go ahead and graph this into the polar curve over here on the right. Notice that in the cosine example, right, all the way in the previous page, we said that the cosine should be something that starts off pointing in the right direction. Indeed, here, we started off pointing in the right direction. Whereas here, the sine function should be pointing not in the right direction. It doesn't quite point up, to be frank, because notice this function up here, it seems to be also pointing up if you start with the second petal. So what happens for these rose petal families is actually what you do is you start at the origin and you start tracing into the first quadrant. Let's see why. The first point is at 0, 0, which we know is the origin. Then what we observe is that from 0 to pi over 3 is 60 degrees, so that's going to be this angle right here. This is theta equals pi over 3, about 2/3 of the way through that first quadrant. I need to have one whole petal. I need to have a whole petal right here. So we're going to start at the origin, and then we're going to sweep through that first region right here. And as I make that sweep, my petal needs to get bigger and then smaller. Then what we have is from zero, we'll label that appropriately, that's petal 1. Then from pi over 3 to 2 pi over 3, which is right here, that's 2 pi over 3. I seem to get a negative petal. So again, like in the previous problem, we have this reflected version of what's happening. And in the reflected world of this upper bit up here, we need to draw a petal. So that's going to be this petal down here. Call that 2, and there you have it, that's 2. Then from 2 pi over 3 to pi, that's going to be this last little region right here. We're going to have our third petal. So that's going to be something that looks like this. Let's call that 3. And what you'll notice is that at this juncture, something interesting happens. You might think that, oh, we're going to draw over here, and we're going to draw up here and over here. But that's not quite the case. Let's see what happens. Between pi and 4 pi over 3, pi and 4 pi over 3, remember, 4 pi over 3 is right here. So that's only, this consideration, this petal right here, is only in this region. Notice that this is a negative petal, so we care about the reflected version. I'm talking reflected like across the entire area. Notice that if I were, you don't have to highlight this, but if I were to look at this region, which is what I'm interested in, and I were to look at the opposite spoke to that, it would have to be this one. Those are opposites of one another. So if I have to graph this negative petal in the opposite region, notice there's already a petal there. So this is going to be an instance where, indeed, we're going to end up redrawing over the same petal again. So this petal right here, which we're going to call 4, actually is a petal that's drawn all over this first one. So in fact, that's already there. This is 1 and 4. Then similarly, 5 is going to get shared down here, and 6 is going to get shared over here. So in this case, what we see is that, in fact, we have drawn this function twice from 0 to 2 pi. And that is going to be the fundamental difference. One of them we graphed once, the other one was graphed twice. Moreover, if we can make this observation, we can say, oh look, this inside period number, 3, is odd. And we see how many petals? In this case, 3 petals. So let's take stock of what we see here. What we see is, if we do a compare and contrast here, what we see is that for the cosine petals, we start on the theta equals 0 axis. In the sine ones, we start in the first quadrant. What we see is that when the inside petal number is 2, meaning it's even, we see twice as many of those petals, and we only trace once. Whereas when the inside period shift change number here is odd, we see exactly that many petals, because in fact, they were all drawn twice. So in both cases, here 2 produced 4 petals, here 3 technically produced 6 petals, as we saw over here. The difference is that when the period number here is odd, half of those petals overlap with one another. So whereas in the even case, we get twice as many visible petals, in the odd case, we get exactly that many visible petals. This is all collected here in this statement, where we observe that the rose petal family are given by r equals a sine n theta, starting at the origin because it's a sine and it moves into the first quadrant, or r equals a cosine n theta, meaning we start on the theta equals 0 axis. If n is odd, we get n visible petals because of the tracing twice. Whereas if n was even, we get 2n visible petals because of the tracing once. And the length of each single petal is, of course, whatever that constant coefficient a, which affected our amplitude. Now, one thing you can notice, if you actually go back in time, you can look at this previous one, this tangent to the pole type trig polar curve. You can look at that and you can say, well, this got traced twice, and these got traced twice. Is there a reason these are related? The answer is, well, of course there is. If I come to take a look at, for example, these formulas up here, observe that, in fact, this can be thought of as cosine, 2a cosine of 1 theta. Notably, 1 is odd. So there is 1 visible petal traced twice from 0 to 2 pi. Using the new idea we have. So, of course, yes, we do get traced twice. And yes, this is actually referred to as a petal, which is great. So the circle family, well, 2 of them anyway, really aren't their own object. They're technically just rose petal families, these 2 on the right. So the circle family really should just be this one single circle. But at the end of the day, what we can notice is that the circles that we have here having 1 petal, those are bona fide circles, so they can fit into the circle family. What we saw here is that when we start increasing the number of petals, it starts squishing them into more like petal-like shapes. So although when the coefficient here is 1, we are technically part of the rose petal family, typically we just lump it into the circle family. So we've introduced so far the circle family and the rose petal family. The remainder of this handout is going to be dedicated to introducing the additional families of polar curves that we can encounter, for example, the limacons. So we'll pause here for now and we'll take up the next page at the start of the next video.